kilogram squared. So if we calculate that, our mass of TNT, our equivalent mass of TNT then, right? That blew up is 3048 over 6 to the power of 3, and that is 131 roughly kilograms of TNT. Okay, and then we add this equation mTNT, the explosion efficiency times the mass, or explosion or combustion energy, and the energy of TNT. Okay, so there's something that they haven't done in the book, because if you do this accurately, your explosion efficiency, or we're gonna do this, approximately equal to our delta H of combustion, is actually negative. 802.3 kilojoules per mole. So either this is also negative, which is not given via ET&T in the book, is given as 4,686, and that is in kilojoules per kilogram.
Huh?
So there's a sign error somewhere. Yes? Right, right. So they have just forgotten about that when they set up this equation. So ET&T should be negative, right? Or what I'm saying is that it's not listed like that in the book. But you can't get a negative mass, so they just forgot about the sign. It's supposed to be an explosion energy. So I think that, so it's an absolute, right? So the most appropriate would probably be to put a negative up here, right? But I think that you're not gonna be confused on that, because you know that you can't get a negative mass that doesn't exist, right? So you just remember that you put positive. The only thing that you need to watch out for is that the heat of combustion that's given in the book is in kilojoules per mole. This is in kilojoules per kilogram. So you do need to adjust for the molecular weight. So our delta HC, I'm going to call it negative delta HC, is equal to 802.3 kilojoules over 16.74 kilograms per mole. And this is kilojoules per mole. And Rm, in other words, the methane that exploded, then is equal to the equivalent mass of TNT. It's 86, so this was kilograms, over the explosion efficiency times, it turns out to be 5.0 times 10 to the 4 kilojoules per kilogram. That is the heat of combustion. Okay, so that is equal to, let me see, 12.284 over the explosion efficiency. Okay, so in other words, our mass then, right, would be somewhere between 123, say, to 1,200, right? So this is if we have an explosion efficiency this case, right, we weren't given the explosion efficiency. You take the average. We would be at about 245 kilograms of methane. Okay, so that's a significant amount of methane, right, that exploded, but it did destroy a house structure 100 feet away from the explosion.
It seems kind of weird because if efficiency is 0, then you need like
You would
infinite
not have
limits.
an explosion efficiency of 0, right?
Yeah, but I mean, but based on the formula, it's like saying it's releasing energy. Because it's at the bottom.
So
So that doesn't make sense.
I inverted this equation was for mass of TNT, right? That has an explosion efficiency times the mass. We were just using we were using it backwards. We weren't saying that we had 30 tons of ammonium nitrate and asking what is the destruction of that if you assume an explosion efficiency. We approach this problem backwards, right, in terms of right, how I would look at this, because you know what you might want to do at some point, if you know you have your company is storing a certain amount of material in a bin and you're worried about, right, what if that explodes? Because then you can use the equation, but you would use it, right, you would have the mass in that case. And you would go back, you would look at what is the equivalent mass of TNT that would be, assuming a certain explosion efficiency. And in that case, you probably want to pick the 10% explosion efficiency as the worst case scenario, right? Because then you will calculate, you know, whatever, at a certain distance, if you know that there is a residential community a certain distance from the plant, right, you can look at the scale distance and go into this one and see what overpressure and what damage you could expect at that point. So I would say you would be more likely to use the equation that way than sort of this way, where we had an explosion and try to back out how much actually exploded. But of course, a lot of times that's all you have. In this case, in West Fertilizer, you heard the CSV people say they didn't. There was nothing left to determine was caused the fire. Right? There's nothing left. It all went up in the explosion, so they don't know what actually caused the initial fire. But clearly, they had a lot of flammables in there. Right? So, any questions on this? Oops, that's all the problem. So the next thing, we're not gonna get through this today, but I wanna get it started for you so that you can take the flammability diagram and practice until we meet next time. I think I did, and I also next time wanted to talk about methanol, because it's often used, or it has been used. It might be banned from use at some point, but it's used in school demonstrations and in museums. But it's unfortunately a very flammable chemical. Okay, but in this case, methanol is stored in a vessel. It's vapor is inerted with nitrogen to total pressure, again, a 4-inch water gauge. And we're asked the same thing as we worked on the last time, but for benzene. Okay, we drew the flammability diagram for benzene. Now we're going to do the same for methanol. Okay, and see, do we have a flame? Obviously, if it's inerted with nitrogen, what we start with is not flammable because it's under nitrogen. But if this nitrogen methanol mixture leaks out, will it become flammable? or is the vapor pressure such that we're actually below that limit? And most often you're not that lucky. That's the bottom line. So we are asked to determine what would a safe methanol concentration be, and that I'm sure we're gonna have to leave till next time. Okay, so what do we need to do? Maybe I should get the list up on, right, what we need to do. So we need a flammability diagram first, okay? Because what we need to do is determine the flammability zone on this diagram. Blank one. And let's see what information I put on the slides. Oops. Okay, so what we want to do, we want to draw the airline, mark the upper and lower flammability limits on this airline, and then we need some more information, right? We need the upper and lower oxygen limits. We need a stoichiometric line. We need a limiting oxygen concentration. And there are some of that information is available in tables. Others is not. If we just look at, just to get you started, here, I'm gonna let you find the upper and lower flammability limits, okay, just so you can practice where the table is. But you're gonna need upper flammability limits, lower flammability limits. They're available in the appendix. For methanol, there is a limiting oxygen concentration in table 6.2. So in this case, this problem actually does not ask for the entire flammability diagram. So what you can do is, once you've drawn the airline, right, and you mark the upper and lower flammability limits, all you need to determine is this triangle, right, which is going to be where, okay, I'm just drawing by random now, where the LOL, limiting lower oxygen limit, and the lower flammability limit, air, meets the limiting oxygen concentration, or the stoichiometric line. Okay, now I haven't drawn the stoichiometric line, so we need the stoichiometric line, which we determine from, right, we want methanol to go to CO2 and water. So we need a point here and a point here to draw the stoichiometric line. Okay, so we need 1 CO2 and 2 water, so we have 4 oxygens there, which means that the oxygen concentration on the stoichiometric line would be 2 over 2 plus 1. 2/3. Okay. 0.6, 7. Oh, what did I do? Uh-oh. There are 4 there, and now I have 5 on this side. 1.5. Called 3 ones. I need 3. So we have, what did I say? We have 1, 2, 3, 4. This is right. It's just that one. So we actually have, it's 1.5. And there's 1 plus 1.5. So that's actually 0.67. So that's the oxygen concentration. If you have a stoichiometric mixture, no nitrogen, so it would be 60% oxygen, 0 is up there, right? And then you draw a straight line down to 0. Don't copy this one. Draw it on your diagram. Okay, so the slides from last time is up on Sakai Canvas. Sorry, I've used Sakai for years. So let's see if you can do this one. Obviously, I'll go over it all next time we